So hello and welcome to this video where I'm going to discuss question from rigid body motion. So we are given that a circular disc is moving on a horizontal surface. The radius of the disc is given. The horizontal surface is taken to be the xy plane. Okay. And then at a particular instant the velocity of 2 points which are on the rim of the disc, two diametrically opposite points A and B on the disc are given. Velocities are given VA and VB. So for the same instant, we have to find a number of things. The first thing being the position vector AB, uh, the angular velocity of the disk, the velocity of the center of the disk, and then if I were to draw a diameter perpendicular to AB, then its ends are called C and D, and we have to find the velocities of C and D as well. So let us proceed, starting with the first part. So I have drawn a diagram. Velocities of A and B are given, two diametrically opposite points on the rim of the disk. Now, how do you proceed to find the vector AB? So you can find it in the way that the velocities of A and B uh, are not free to be anything. Like if you were to take any two particular vectors, right, uh, for velocities of A and B, those vectors, those velocities will definitely give you a clue about the direction of the vector AB. Why? Because the distance AB is fixed, and therefore the velocities of A and B parallel to AB must be equal. So if A is the components of velocities of A and B, which is along the line AB, are unequal, then the distance will immediately change. So if you look at a differential time instant, if you imagine, uh, this is the starting instant that we are given, and if you look at an instant which is a time interval dt later, and if the velocity components of A and B parallel to AB are different, then immediately the distances that they move in that dt time interval parallel, their displacements parallel to AB will be different, and therefore immediately the distance AB will change. And so this is a constraint on the velocities that their components parallel to AB must be equal, and that leads us to the conclusion that if we subtract the velocities, the difference will be perpendicular to A. So because their parallel components are equal, that when we subtract them, the parallel components disappear. They cancel each other out because they're equal uh, in magnitude as well as direction. And therefore only the perpendicular components remain. And therefore the difference of VB and VA is perpendicular to AB. So I just simply subtract and I get that VB minus VA is 6i minus 8j, and then I conclude that AB must be perpendicular to this vector VB minus VA. Now if I have this vector VB minus VA, which I have drawn here with the red pen, 6i minus 8j, how do I find a vector which is in the plane, xy plane, which is perpendicular to this VB minus VA? Obviously I have two choices, and I call these choices D1 and D2. Now how do you arrive at a vector which is perpendicular to a given vector in the xy plane? How do you, in other words, rotate a vector by a right angle, either clockwise or anti-clockwise? And let us look at that over here. How do you rotate a vector by a right angle? The first step is exchange the x and y components. So you can look at the example straight away. So if I have the original vector minus I plus 6j, I want to rotate it by a 90 degrees angle, either clockwise or anti-clockwise. The first step is I exchange the x and y components. So it becomes minus 6, it becomes 6i minus j. And then after you've done that exchange, if you multiply the x component by minus 1, you get an anti-clockwise rotation. If you multiply the y component by minus 2, you get a clockwise rotation. So this is a very simple scheme, and very powerful and useful scheme, which can be used in multiple places in physics. Uh, that how do you rotate a vector by 90 degrees? You obviously don't change its magnitude, you just rotate it. Um, and you can see this and you can memorize this, or you can also try to understand it. You can try to prove it using complex numbers, because in complex numbers we know that the multiplication by iota is an anti-clockwise rotation by 90 degrees, and so on. So coming back, I apply this scheme to this vector v2 minus v, and I rotate it. Once I rotate it clockwise and anti-clockwise, and I can choose any of these two for the vector AB. AB can be any of these two. Um, so this is how far we can deduce it. We cannot go further than deciding between these two. The, we cannot decide between these two vectors using the given information. So we just choose whatever we like. I just choose D2 because it has positive 8 and positive 6 to be more comfortable with the calculations. And of course, D1 and D2 give us the direction for AB, but the magnitude of AB will be the diameter of, of the disk, and the diameter of the disk is 10 units, and by happy coincidence, the magnitude of D2 is already 10. And so I finally decide that the vector AB must be 8i plus 6j. Of course, it is one of two choices. I could have taken minus 8 and minus 6. So I choose this one and put it in the red box. This is the first step. We find the vector AB from the velocities VA and VB. It's quite interesting. The second step uh, is finding the angular velocity of the disk. Now this is the more critical part of the video, more interesting and the more central concept that we are going to learn. So the central concept here is that any point on the rigid body, on any rigid body, this is a basic property of a rigid body, is that any point on it, when it is observed from any other point on it. So we have 2 points on the rigid body, just like we are given in the question A and B. So if I look at the motion of B from A, from the perspective of A. So if I sit on the point A and I keep moving with the point A, so the velocity of B will be obviously perpendicular to AB, and B will move in a circular path. It's very simple to see this because the distance AB is fixed, so B cannot move in any way other than a circular path around A. As seen from A. As seen from a laboratory frame, from a ground frame, B can have a complicated path. It can move in a cycloid, it can move in a straight line, in a number of ways, it can move in a circular path. But from the perspective of another point on the rigid body, any other point, it's not only about the point A. If I were to put any 2 points on the rigid body, the motion of one of them as seen from the other would have been a circular path. So that makes sense. And that circular path motion has an angular velocity, obviously, and that angular velocity is the same for any such pair of points. So if I look at the motion of point number 3 relative to point number 1, it will be a circular path with angular velocity omega. If I look at the motion of point number 7 relative to point number 2, it will be a circular path with the angular velocity omega. The angular velocity will be common. The angular velocity in all those cases will be the same, and that is what is known as the angular velocity of the rigid body itself. Uh, so that is what we have to find here, and for that we can easily exploit this same thing, that if I look at the motion of B from A, it will be a circular motion. So because of that, I look at this V equal to R omega, that if so I'm now looking at the situation from the point of from the frame of reference of A. So in that frame of reference, the velocity of B is, I call it V, and the distance between them I call R. So V equal to R omega must be true. And the vector form I write it as, I put it in the red box. Now, that omega vector is perpendicular to the plane of rotation of the disk, and R21 is the position vector of the point uh, 2 relative to 1, right, as I've shown in the diagram over here. And so if I look at the diagram, if omega is an anti-clockwise rotation, then the omega vector is pointing out of the plane. Omega vector points out of the plane, and this follows from the right hand rule. And then if I'm given that this is the position vector of the point 2 relative to 1, and the omega vector I'm given the angular velocity vector, the simple result is that the velocity of the point 2 relative to 1 will be the cross product, omega cross R2. And we know the scalar form of this relation very well, V equal to R omega. But this is the more powerful vector form, which encapsulates both the magnitudes of the quantities and their directions. So omega can be anything, but in planar rotation, which we are dealing with right now, omega is a vector um, which is perpendicular to the plane of rotation. So we are dealing with planar rotation, and therefore omega and R21 will always be perpendicular because we are looking at a planar body. And if we are looking at a planar body, then uh, so if the body is entirely in the xy plane, for example, R21 will be a vector in the xy plane, whereas omega will be a vector perpendicular to the xy plane. So they are always mutually perpendicular, and because of this property that they are mutually perpendicular, uh, we can use the cyclicity of the cross product. So the direction of V, omega, and R are mutually perpendicular. Their directions are mutually perpendicular. Directions are designated by caps over the letters. So omega cap means the direction in which it's a unit vector in the direction of omega. So I can change this relation. I can cyclically change this relation uh, to the second one. Omega cap equals R cap cross V cap. This is only allowed if all of them are mutually perpendicular. Otherwise, it's not allowed. So this works exactly like the unit vectors along the x, y, z directions I, j, k, which are also unit vectors which are mutually perpendicular. And if we do that, and we also look at the scalar relation, which is omega equals v cross r, we get a very simple relation for omega. It's not very complicated to see how we arrive. We just put the two relations together: the directions relation, the relation between the directions, which is omega cap equals r cap cross v cap, and the scalar relation, which is omega is equal to v by r. And we get this nice relation which I put in the red box. And what this relation is telling us is that if I have 2 points on a rigid body and I know that I know their relative velocity, which is v21, which is simply their relative velocity, and I know r21, which is their relative position, which is the position of 2 relative to 1 as seen from 1. The position vector of 2 with 1 being the origin is r21. If I know the relative position, if I know the relative velocity, because of this property of rigid bodies that their distance must be fixed, this is the only property that I've used so far. Using this property, I get this relation. But this is only valid if omega is perpendicular to r21. This is a very important relation. It's a very important condition for this relation to be valid. That this is for planar rotation, where omega is always perpendicular to the vector r21. So the body remains in a plane body moves on a plane. All the points of the rigid body are in the same plane. Uh, they don't leave that plane. So it's a planar kind of motion and planar rotation. So using this relation, I simply get the omega in this particular case, because I know the Vb minus V, which is a relative velocity. I know AB vector, and because I had two choices for AB, uh, I also get two answers for omega. If I took the other version of AB, which is the minus 8 minus 6 version, I would have gotten omega equal to plus 1 k cap. So I get two versions of the situation, which both fit the given information, because we are only given VA and VB. Um, there are two possibilities, and one of them is a clockwise rotation, and the other is an anti-clockwise rotation. So I'm going with the clockwise rotation here, which we know to be true because omega is a vector which points into the plane, right? So, and I know that because I've drawn AB and VB minus VA, assuming that the x-axis is towards right and y-axis is upwards. So omega is clockwise. So now moving on, um, now we must find the velocity of the center of the disk, and so we use the same result, it's the same scheme, it's the same method that. So going back to the previous slide, so these two formulas in the red boxes, what they are telling us. The second one is saying if you know the relative position of 2 points and the relative velocity, you get omega straight away. The first one is telling you that if you already know omega and you know the position of one point relative to the other relative position, you can find their relative velocity. And if you can find their relative velocity, if you know the velocity of one of the points, you can also find the velocity of the other point. So this is the concept that we use over here, that I already know the velocity of A. So if I find the relative velocity of O, velocity of O relative to A, VO minus VA, which is easily found from that result, omega cross AO, um, then I get VO. And so this is very simple, because AO vector is half of vector AB, because it points in the same direction and it has half the length. Uh, so from this simple scheme, I get VO minus VA, and from that I get VO, the velocity of the center of the disk. And so now, what this tells us is that if I know the position at this particular instant, and definitely remember that all of this is being done for a particular instant. As soon as we allow time to move on, just a fraction of a second later, all these velocities would change immediately, um, except for the velocity of the center, because that is, if the disk is uniform, the center is the center of mass, and if, assuming that it is a free motion, that there are no external forces, the velocity of the center will remain the same, but that is the only point. All the other velocities will change, the positions will change, the vector AB will change, the vector AO will change, everything will change. So this is just an instantaneous analysis, but this is the first step towards a more general analysis. So the lesson from this calculation of VO is that if I were to know the position of any point on the disk relative to A or relative to B, I can get the velocity of that point because I know omega now, and I can use the result that the relative velocity of any two points equal to omega cross their relative position. So, but another method, so that method is perfectly fine, but another acute method that I can show over here is that because O is the midpoint of A and B, O is the midpoint of A and B. If I just take the time derivative of this vector equation, Rho is equal to Ra plus Rb by 2, I just take the time derivative. So the velocity of O is nothing but the time derivative RO. So what are RO, RA, and RP? They are position vectors of O, A, and B relative to some origin, relative to an arbitrary origin. Uh, but we are sure that the time derivative of that position vector will be the velocity, uh, regardless of the origin, of the choice of origin. So if I take the time derivative right, I'm sure to get this relation that the velocity of O will also be an average of, of the velocities of A and B. So I get a quick answer. And just to show you an example, that in a similar way we can find the velocity of a point P, which divides the ratio, divides AB in the ratio 1:3 by the same method, uh, because the relation between the position vectors is replicated in the relation between the velocities, because it's just a time derivative away. Moving on to the last part, which is something that you can do on your own. This is the last part you should try on your own. If you've seen the video until now, you've seen the first 3 parts, you know what is going to happen. It's just a little more complicated from calculation wise. But the last part is where you can say you put all the pieces together. You learn all the techniques in the video and then you practice them and then you put all of them together. So the last part is a nice exercise. So we have point C and D, which are on diametrically opposite points as well, but that diameter is perpendicular to AB. So again, if I want to find the velocity of C, I already know the velocity of O, and if I can find the vector OC, then I'll just take the cross product of that vector with omega. And this is what we have done. So I already know the vector OB, which is half of AB. Then I rotate it by clockwise, by 90 degrees clockwise and clockwise, which is also something we have seen in the video. So we arrive at the vectors OC and OD. Using those vectors, we arrive at the relative velocity. The velocity of C relative to O, and the velocity of D relative to O. So it is just an application of things we've learned in the video. So we arrive at these answers. Now to summarize what fundamentally we've learned 3 things. One thing we have learned a neat and beautiful technique how to rotate any vector by 90 degrees clockwise and anti-clockwise. And after that, we have learned the central concept of this video, which is these 2 equations. The first one being that the relative velocity between 2 points is just the cross product of the angular velocity and their relative position, which is just a mathematical expression of the fact that, as seen from one point on the rigid body, any other point is moving in a circular path, and the angular velocity of that circular motion is common for all these motions. If I look at one point relative to another, so if I have 10 points on the rigid body, if I look at point number 10 relative to 5, I look at point number 7 relative to 3, and so on. And the other way as well. So if I look at 7 relative to 3, if I look at 3 relative to 7, all of them are circular motions. And what is common between them is the angular velocity, which is common. That is the angular velocity of the rigid body itself. That is the angular velocity we know to be, we are familiar with the concept of angular velocity. So to summarize, these 2 equations are what we have learned. The first one is a very general relation, it works always. And omega can be any vector in general, because in planar rotation, omega and R21, these 2 vectors are perpendicular, they are mutually perpendicular. And therefore, the relative velocity, the omega, and the relative position, all of them are mutually in planar. But in 3D, there is no such constraint, omega can be anything. And always remember that this is again an instantaneous analysis. So omega can be anything. So the first equation works always, but the second equation is generated from the first equation under the assumption that omega is perpendicular to R21. And if omega is perpendicular to R21, then omega, R21 and V21, which is just V2 minus V1, they are all mutually perpendicular. And so the second equation only works under the assumption that omega is perpendicular to R21, or it only works for planar rotation, only works for two-dimensional motion, you can call it, uh, right? And so this is what we have learned. And thank you for watching and hope you enjoyed the video.